one way, which if you've had a physics class, it's like when you have orbital angular momentum and you take the tensor product of two representations of a given spin, it decomposes into a sum of other representations. It's the same thing. That's kind of confusing, probably for people who haven't done it, or even for people who have done it. So let me just think. Let's just think of them as like qubits. So an anyon is like a qubit in the following sense. If you one qubit, it's a two-dimensional system. If you have 2 qubits, it's a 4-dimensional system. 3 qubits, an 8-dimensional system, and so on. Anyons are a little bit different. So if you have one anyon, I don't know. I guess it'll be a 1-dimensional system. So the anyons, I'll describe the states by pictures like this. And so different dimensions will have different pictures. So with one anyon, I'll have a picture, and I'll label the edge, and I can label the edge either by 0 or by 1.
How are you labeling it?
Depending on the state it's in?
So it turns out there's many different models of anyons. There's not just one that's correct.
Mm-hmm.
So for now, what I'll talk about is one called the Fibonacci model, because it's interesting. But there's many other ways of doing it. So in the Fibonacci model, the labels are either 0 or 1. And 0 here is interpreted as vacuum, as in there's nothing there. And 1 is interpreted as there's something there. Okay. Now this is interesting. That's kind of boring. But when you have 2, it gets more interesting. So when you have 2, you can describe the state by a picture like this. Or again, so these can all be labeled by 0, 1, 0, 1, 0, 1. So you'd think that would give you a 4-dimensional system. But in fact you don't, because only certain combinations are allowed. So in fact, let's see. So I'm also going to label this edge here. And the intuition here is that these are sort of particles.
Okay.
And this is also a particle. This is what you get when you zoom out and you sort of merge these together.
It's like a logical qubit kind of thing. Just like how you zoom out physical qubits and you get logical qubits.
Well, I mean, when you zoom out on the surface coder, you still have another code. And so the topological system, when you zoom out, it's still a topological system. I'm just saying, if you take these 2 particles and you zoom out far enough so that they're combined into one, what particle do you have? I mean, another example is if you have 2 spin 1/2 particles, and you zoom out, you get a particle that either is spin 1 or spin 0. And that's the same thing that's happening here. So the rule is, what's the rule? 0 cross 0 is equal to 0. 0 cross 1 is equal to 1 cross 0 is equal to 1. So what am I trying to say here? 1 cross 1 is equal to 0 plus 1. So what I'm trying to say here is these are the allowed fusion diagrams. This is algebraic. But so what I'm saying is 1, 2, 3. I'll just try to draw all the allowed combinations. So I could have 0, 0, 0. So that means there's nothing there. 0 is empty. I could have 1, 0, 1. So the interpretation here is this 1 means there's a particle there. There's not a particle there. So when you zoom out, you still get a particle. That makes sense. So these first 3 rules make sense. Same thing. If you zoom out on one particle, you get one particle. The last rule doesn't make sense.
1, 1, 0, and 1, 1, 1.
Yeah. So both of these are possible, not just one or the other. Again, this is like the spin 1/2, spin 1/2. And so either when you zoom out, you could end up with a vacuum state, or you could end up with one particle. That's degree of freedom.
Is there never a chance that when you zoom out, you see 2 particles?
No, because you're zooming
Okay.
out into just
Okay.
yeah. So the number of states it look like is, so here we got our table, n the number of quasi-particles, the number of particles or quasi-particles, and let's say d the dimension, So if there's one particle, the dimension is 2. If there's 2 particles, the dimension is 5. If there's 3 particles, so if there's 3 particles, sorry. So here.